Hello, Mr. Aaron, Mr. Ryan, are you right?
Yeah.
Okay, so we given two rows of numbers. We want to find out the maximum number of lines we can connect the numbers from the first one to the second row. Same number, we can put it together. And the requirement is that one number can be only used to connect to one line. Okay? One number. So for example, this one has been connected to this one. So it cannot be used to connect to another one.
How about 2? You could do 2 and 2.
That's a good question. 2 and 2 here, but there's crossing here. We don't want the lines to be intersecting. So
Yeah,
we want to find out the number.
What if you have one that has no numbers?
What if you
Good question
have,
and zero.
what if you have like 1, 4, 2, and then you had 4, 2, 1.
Okay. So
You could do 4, 4 and 2 and 2.
yeah, so that's 2. Okay?
Yeah.
You can't do this because it's intersecting, okay? So we want to find out the maximum number of the lines we can get by connecting the same numbers. Okay, connecting the same numbers. One from the first one, another one from the second row. And each number can only be used to connect to one line only. Okay? That's very important. Okay, so for example, if there's a 2 here, you can't connect it because this 2 has been used
what
once.
if they have like uneven numbers?
1, 2, 3, 4, and then 2,
What?
3.
Yeah.
Okay, 2.
What
So any question about these questions?
what if you have nothing?
Then nothing, then 0.
But what if both of them are nothing?
Then 0.
But wouldn't it pair up?
That's a good question. That's more like a philosophy question, yeah? If you can you connect the two empty things? Is empty thing a thing? If it's empty, then 0. Simply return 0, okay?
Let me try 0 and
Any more questions
it
about?
doesn't do it.
Okay, come on.
It has to be 1 to 2,000.
Okay, so any more questions about this problem? How would you try? Right? The computer is very good at trying, right? That's its advantage. So, for example, this one, right? We can ask computer to pair up every single one and try the next one, and try the next one, try the next one. Am I right?
Yeah.
Okay, let's consider this example. There's a few numbers here, and then here this is 2. There's a few numbers here. There's 1, 2 here, the other 2 here. Okay. So look, this is the end. Which 2 can we pair to these two to? This one or this one, right? There are 2 choices. So which one should we choose to pair these 2 to it? This number and this number is 2. And there's
But the
another 2
right
here.
one.
This one, yeah?
Yeah.
Why not this one?
Because you might have another like 2 like left here, let's say, and then you won't be able to.
Very good. That's what I want to hear, right? So look, we can try from the right to the left or left to the right. If we know this number is equal to this number, we can just greatly pair it, right? We can just use it. If we don't use it, then there could be an intersection that later, right? Yes?
Yeah.
Okay. Then if this number is not the same, if this is 3, so what do we do? Look, if this is the 3, then we can't pair, obviously, right? So either we pair with these, or we pair with these, right? So there are only 2 possibilities. If you don't match, okay, and let me write another one, which is 3, okay? And there are a few numbers there, I don't care. Okay, so this number is not equal to this number. So the answer, the maximum number, the ultimate solution is that we remove this and then we try to see if it pairs up. Or we remove this number to try to see if it pairs up. There are only 2 possibilities, am I right? And we find the maximum.
So you're saying that we basically go through. So you try one time with the 2 paired up.
Yes, look, this is 2 random numbers. Let's just consider the last 2 numbers. We compare these 2 numbers. If it's the same, if this is 2, then we can just connect it, right? And then we solve the smaller problem, right? If it's not the same...
Yeah, but what if there's like something over here?
No. Let's try. Okay, there's something over here. What I'm saying is that we consider the last 2 numbers, right? Okay, this is the case, right? General case, right? These 2, suppose, are the rightmost number. Okay, Okay? Yes?
Yes.
How many possibilities? There are two, right? Equal or not equal, am I right?
Yeah.
If it's equal, we connect it, right? And then we have a smaller problem.
Yes.
If it's not equal, we get rid of this number, right? Yeah, because this number cannot be connected to any of those because it will be intersecting, right? If you connect it there, it will be intersecting, right? So we can get rid of this number. So this is another problem. Or we get rid of this number. This is another subproblem. And we compare which one can we get. Alright? And then we keep doing this.
But that would take more time.
That's fine. We just recursively divide it into a smaller problem, right?
Yeah, but if both of the ways are the same, then you'll be just like wasting time.
I know, but we can use the cache to remember, right? Remember, this is the dynamic programming. We use the cache to remember the intermediate result, okay? So, this is the number one, right? Number one, array one. This is the array two. Then we use the function dpij. I is the index of the first number. J, this is index I. This is index J, okay? So it means that the maximum number of lines we can connect from the left to the index I inclusive, okay? So there are only two possibilities. If array 1, the number is equals to array 2, J. If these two numbers are the same, the answer is return dp I minus 1, j minus 1 plus 1, right? If this number equals this number, the answer is this dp I minus 1, j minus 1, right? Plus 1. What's 1? Why 1? If this number equals this number, the answer is dp I minus 1, j minus 1, which is this problem, plus 1.
You covering it?
Yeah, that's the one. Okay, good job. Otherwise, the answer is the maximum of dp I minus 1j or dp I j minus 1, right? These two cases, whichever is bigger. Right? 1, 2, 3, 4. 4, 5, 6, 7. This number is not equal to this number. So the answer is dp I minus 1. Minus 1j, so it's this problem, or dp I j minus 1, which is this one. Whichever is bigger, okay? And if we're reaching the end, if I or j is smaller than 0, we return 0, right? So we have to check the boundary. If I is smaller than 0, or j is smaller than 0, then return 0. And define this dp I j, right? Okay? So that's it. The missing part is, what's the keyword? Cache, right? Yeah.
Cache TV.
Dynamic programming, top down. This is quite similar to Fibonacci number, right? Yeah, remember the Fibonacci number? We have repeated intermediate results. And then we need to save it. So look at ij. So basically, ij, right? So we can have a table. This is I, this is j. Right? If I is smaller than 0, j is smaller than 0, then it's 0. Otherwise, let's take a look at this example, okay? 1, 4, 2. 1, 2, 4, right? Yeah? The answer is 2, right?
Yeah.
Okay, so the I would be 0, 1, 2. 0, 1, 2. J will be 0, 1, 2. This is I. This is J. Okay, this is I, this is J. Okay, when 0, 0. 0, 0. If it's the same, then it's 1, right? 0, 1. Right? We want to calculate 0, 1, right? So it's equal to this one. That will become minus 1. It will be minus 1, 1. Then that's 0. So it's 0, 0. So which is 1 here. Make sense? So we can populate the numbers this way. Okay, let's take a look at this example here. It's 1, 1, right? It's 1, 1. 1, 1. Which is this one. Not equal. So it would be...
What's the 1101?
It's the index. So this...
Yes. So...
Okay.
Oh, yeah.
You got it, right? So this number, I want to find out the value of this number. So it's the I-1j or ij-1. So it's basically this number and this number, whichever is bigger, right? If it's not equal, right? If it's equal, then it's this number plus 1, am I right? Yeah?
Yeah.
Does it make sense?
Yeah.
We want to find out this number, 2, right? 2, which is 1. If it's the same, if these two numbers are the same, then it simply is this number plus 1, right? If it's not the same, then we have to find out this number and this number, and this equals the maximum of it. Make sense? This is what this equation is. So we are populating it. So why we need a cache? Because some values we might need it several times. So the first time we find out, okay, this number is 2, for example. Then the next time when we need this number, we don't need to find out we don't need to calculating it, right? Because we already calculated before, and it doesn't change. So we just use it. This is what the cache is for. So look, dynamic programming, top-down dynamic programming is basically, if you want to find out this number, okay, so we check if it's equal. If it's equal, then this value is simply equal to this value plus 1, right? If it's not equal, then we have to find out the value of this and compare which one is bigger. Then we put the number here, right? All right. It's top-down dynamic programming. We call it recursion with memoization. Memoization. Remember. Where is the remember part? Cache. So this is from left to right to the left. We can do it from left to the right. It's similar, right? 1, 2, 3, 4, 5, 6. We can check this one, right? If it's equal. If it's equal, then we connect it and move it to the right. If it's not equal, then it could be this way or this way. Am I right? Is it the same? By connecting the lines from left to the right and right to the left, it's the same, right? Same thing, am I right? Why is it the same thing? 1, 2, 4, 1, 4, 2, right? Is this the same as 4, 2, 1, 2, 4, 1? Is it the same? Is it the same?
Why do you need to reverse it?
That's what I'm saying. Is it the same? The answer, yeah, of course it's the same, right? We just image mirror it, so it's the same.
Yeah, but why do you need to do it?
No, I don't need to do it. I'm just saying it's the same. That's why we can go from left to the right or right to the left. This is from right to the left, right? Because minus 1. If it's left to the right, we need to plus 1. And check the boundary. If we this is crossing the left boundary. If we go from left to right, we have to check if I bigger or equal than the length of the first or the second array, right? Okay, what have you learned today?
About crossing, and we have this thingy, and we need to can't cross over line we connected of the same number.
What solution do we have?
Dynamic programming.
Dynamic programming. What's dynamic programming anyway?
Memoization.
Memoization. What's dynamic programming?
Top down, bottom up.
I know if you want to explain cache,
Cache TV.
These are the techniques in dynamic programming, but what's dynamic programming? It's a technique. For example, like, how many pens do you have? You take it. How many pens you have?
3.
How many pens are all together?
4.
How do you get it 4?
3 + 1 = 4.
3 plus 1 equals 4. That's dynamic programming. You're not counting from beginning 1, 2, 3, 4, right? So dynamic programming is basically dividing the problem into smaller problems, sub-problems, remembering, memoization the smaller problem. Yeah.
I think I got 5, not 4.
Remember the intermediate result. We solve the smaller problem and we remember it and use the result of the smaller problem to construct the answer for the bigger problem. This is called dynamic programming. And it's top-down. We can have top-down and bottom-up. Top-down, which is recursion with the memoization. And tomorrow, on the next one, we talk about bottom-up, which is reverse. Okay, so look, top-down, because we want to calculate this value, right? So we go this way. Bottom-up, we fill this number, we go that way, right? Makes sense?
Then what's the point of putting up and down at the end?
Just two different ways of solving the problem.
But why is it called top down? Can't it just be called top?
Top down, right? Look, this is top down, bottom
That's
up.
diagonally left.
I know, this is just, for example, like a tree,
Doesn't
right?
go down.
The tree, right? Top down, bottom up, right? If you want to calculate this value, you can do the top down. If you want to find out this value, you need to find out these two values. In order to find out this value, you need to find out these two values. This is top down. Bottom up, you want to find out this value. You find out the value of this, find out the value of this. And then with these two values, you find out the answer. And then this way up, okay? What's the space complexity? If there are I here, J here, what's the space complexity?
IJ.
Well done, because this is the total number of the numbers we need to fill out. What's the space complexity? What's the time and space complexity? It's both I and J, right? Yeah, with the cache, okay? Without the cache, it's totally different story. Okay, with the cache, this is the upper bound, the number of elements we need to fill. We want to complete the numbers in this table. So the space complexity is Ij. The time complexity is Ij because each number we only compute once. Any questions so far?
No.
Okay, that's it for today. Bye bye. Bye bye.
Bye.
Bye bye. Bye bye.